Hey everybody, and welcome back to Front-End Expert. In this video, we will be discussing the events loop, which is oftentimes referred to as the concurrency model within JavaScript. However, this is a bit of a misnomer, because our JavaScript code is actually only run in a single thread. Simply put, this means that our code can only execute one task at a time. So then, how does JavaScript seem to be doing multiple things at the same time? How does it listen to events at the same time as waiting for timeouts and running other code? The answer to this question lies in the events loop and how exactly the browser runs our code. So first, let's take a look at something known as the JavaScript engine, which is simply a program that is able to execute JavaScript code. Each browser has a JavaScript engine. For example, Chrome has the V8 engine. While these are fairly complex programs, JavaScript engines have two primary components, the heap and the call stack. The heap's main purpose is for memory allocation, so whenever our code needs to allocate memory, such as for arrays and other objects, it happens on the heap. On the other hand, the call stack is used for keeping track of the currently executing function calls. This is a stack data structure which is last in, first out. With each function call, a stack frame, as we call them, gets pushed onto the top of the stack, keeping track of that function call and its local variables. Then when a function call ends, so when the function is done executing, it gets popped back off of the stack. To understand the stack a bit better, let's take a look at an example. Here we have three functions, bark, meow, and speak. On line 16, we call the speak function. So this function gets pushed onto the top of the call stack. Then from within the speak function, we call console.log of speaking. This means that we push the call to console.log onto the top of the call stack. From here, the console.log function would run, logging out speaking, and when that function completes, it gets popped back off of the call stack. Then we continue through the speak function, and we call bark, which pushes bark onto the top of the call stack. Within the bark function, we call console.log of bark, which again pushes console.log onto the call stack, this time with bark as its argument. And again, once bark gets logged out, the console.log function ends, and it gets popped off of the call stack. This is also the end of the bark function, so bark gets popped off of the call stack as well. Next, speak calls meow, pushing meow onto the call stack. And just like bark, meow also calls console.log, so we push that onto the call stack. Then meow will be logged out, and both console.log meow, as well as the meow function, will be popped off of the call stack. Now we come back to the speak function, and console.log of done speaking is called, which pushes console.log onto the call stack one last time, this time with done speaking as the argument. And finally, done speaking will be logged out, and that console.log call will be popped off of the call stack. This is also the end of the speak function, so speak gets popped off of the call stack as well. And now the call stack is empty, which would indicate that there is no code currently running. Okay, so now let's revisit our diagram of the JavaScript engine. This works in the simple case that we just saw, but what would happen if we popped foo off of this call stack and instead pushed setTimeoutFoo with a delay of 500 milliseconds? How would our model work? The call stack could just wait 500 milliseconds, but this would mean that we could only have one timeout, and other code couldn't run at the same time while we are waiting. But if we pop the setTimeout off of the call stack, how would we ever know to call foo? The answer to this question is simply that it doesn't work. We need another component to this system for it to actually work. So let me make this a little bit smaller and make some room here. So in reality, the JavaScript engine isn't running our code in complete isolation. It runs it in what we call the JavaScript runtime environment. This environment provides a set of extra functionality on top of the core JavaScript language known as web APIs. These APIs include the setTimeout and setInterval functions, the fetch function for making HTTP requests, all of the DOM manipulation functions, and a bunch more. So when we call setTimeout of foo with 500 milliseconds of delay, it calls a web API. You can think of this as similar to calling any other API. It is code that runs completely separately from our own, and thus outside of the engine. The setTimeout function then completes and gets popped off of the call stack, all while the browser is keeping track of the delay and the callback to foo for us. But then, what happens after 500 milliseconds? How does foo ever get called? Well, to do this, there's one more component we need to add to our diagram, and that is the task queue. The task queue is a queue data structure, meaning that the first item added to the queue is the first one to be removed. I like to think of this as like standing in a line. You also might hear this task queue referred to by other names, such as the callback queue or the message queue, but they are all just different names for the same concept. Okay, so when the timeout delay finishes, the web API queues up the foo function in the task queue. And now what happens is the task queue will wait for the call stack to be empty. And once it is empty, it removes the first task from the queue, so the first one in line, and it moves it onto the call stack to execute that code. So in this case, only once main completes and is popped off of the call stack would foo be moved onto the call stack from the task queue. And this overall process is known as the event loop. The event loop is a constantly running loop that follows a pretty simple algorithm. First, it dequeues a task, then it will execute code until the call stack is empty, meaning that the task was completed. After this, the browser will render any changes to the DOM, and finally it will go back to step 1 to dequeue the next task or wait for one if there are none. One key point here is that rendering doesn't happen in the middle of a task. It always happens after a task has been completed. Okay, so let's look at some examples. Here we have a log world function and a main function. First we call main, which pushes main onto the call stack. Then if we look at the main function, it first calls console.log of hello. This pushes that function call onto the call stack. Then it will log out hello, and finally it will pop off the console log from the call stack. From here, main calls setTimeout with the log world function and a 1 second delay. This first gets pushed onto the call stack, and it calls the web API. The web API will keep track of the delay as well as the callback for us. So this means that setTimeout is complete and can be popped off of the call stack. Up next, main calls console.log of goodbye, so that gets pushed onto the call stack, and we can log out goodbye. Then of course, this call gets removed from the call stack. Now we reached the end of the main function, so main can get popped off of the call stack as well. And now we have an empty call stack, indicating that there is no code currently running. However, once the second is completed, log world would be moved into the task queue. Once log world is in the task queue, it will wait for the call stack to be empty, which in this case it already is, so it gets moved onto the call stack, and log world is called. From here, console.log world would be called, adding that to the call stack as well, and then it would log out the string of world. And then finally, both of these calls will be removed from the call stack. First, the console.log call, because we always start from the top of the stack, and then the call to log world. And this will completely empty the call stack, which means that we are done executing the code. Okay, so that's the basics of how the event loop works. But there's still a little bit more nuance to see. First, what would happen if we called setTimeout with no delay? This is a bit of a confusing piece of code because you might think that it doesn't do anything, but it actually does have an effect. The callback function won't necessarily run immediately. Instead, it will run once the stack is empty and any tasks in front of it have run. This is sort of like giving a function a low priority, saying that we need to run the function, but we can wait for everything else to finish first. So let's look at an example of this. Here we have the same code as before, but the set timeout delay is changed to be 0. As you might expect, we start by pushing main onto the call stack, which in turn will push console.log of hello onto the call stack. Console.log would then log out hello, and once it does, that function is complete, so it gets popped off of the call stack. But then here's the interesting part. We call setTimeout with the logWorld function and a delay of 0. So setTimeout gets pushed onto the call stack, and from here setTimeout would call the web API. The web API keeps track of the delay of 0 milliseconds as well as the callback. And then setTimeout is complete, so the setTimeout function can be popped off of the call stack. But now the web API will say, hey, this is a delay of 0 milliseconds. It's already ready to be moved back into the call stack to be executed. So what it does is it moves this function, the logWorld function, into the task queue. But now logWorld is stuck in the task queue. It cannot move into the call stack until it is empty, which it is not in this case. This means that main will just keep running. So from here we call console.log of goodbye, pushing that call onto the call stack. Then it logs out goodbye, and of course we pop off this call to console.log of goodbye from the call stack. After this, the main function is complete, so main also pops off of the call stack. And now finally the call stack is empty, so the task queue can move one task into the call stack, which will be the call to the logWorld function. This will act the same as before, so it will push the console.log of world onto the call stack, which in turn will log out the string of world. Then once the log is complete, the console log will be popped off of the call stack, as well as the logWorld function will be popped off of the call stack as well, since we are at the end of that function. And now, this is the end of our code execution because there's nothing left in the call stack and we have nothing in the task queue. So the key takeaway from this example is that even though logWorld had a 0-second delay, it still had to wait for the other code to finish before it could be run. And now this brings us to a very important point, and that is that we want to avoid slow tasks in the browser. If a task is extremely slow, it will block the page from rendering, timeouts from calling their callbacks, and a bunch more. So essentially, we just want to make sure that our code isn't ever clogging up the call stack, since we only get one call stack. A good rule to follow here is to keep big computations on the server side, since we usually have more computational power on the server than in the browser. However, if you must have a slow function in the browser, you can use a web worker, which is essentially just a way to run a completely independent program to the main one that is running. Alternatively, you can use a method known as chunking to split up big tasks into smaller ones. And we will see an example of how to do this in a bit, but again, the better solution is to avoid this altogether if at all possible. To understand why this is important, let's look at one more example. Here we have the same function as the original, but we added a call to the super slow function in the middle. You could imagine this is some super slow loop that takes a few seconds to run or something of that nature. So now let's walk through this and see how this changes the output. First, we call the main function, pushing that on to the call stack. Then we will call the console.log of hello, which will push that onto the call stack as well, and then we will log out the string of hello. After that, the console log function will get popped off of the call stack. Next, we call setTimeout with logWorld and a 1-second delay. This is pushed onto the call stack. Then from here we call our web API, giving it a 1-second delay, as well as the logWorld callback. The web API will keep track of this, so setTimeout can safely be popped off of the call stack. Next, we call the super slow function, which gets pushed onto the call stack. And now we just wait. If the super slow function takes a minute to run, then nothing will happen for a full minute, and the UI will be completely unresponsive. During this time, the log world timeout might end, and it would get queued up in the task queue by the web API, but it's just going to sit there in the task queue and wait for the call stack to become empty. Once the super slow function finally does complete, it does get popped off of the call stack, which would mean that we can finally call the console log of goodbye. This gets pushed onto the call stack, and we log out goodbye. Then this would get removed from the call stack, and we have reached the end of the main function, so now we can remove main from the call stack as well, leaving it completely empty. And now finally log world can be pushed onto the call stack from the task queue. This will then call the console log of world, which of course gets pushed onto the call stack, and then after it is pushed onto the call stack, we log out the string of world. Then we can remove console log world from the call stack, and the log world function would be over as well, so we can also remove that from the call stack. And with that, our code execution would be complete because there is nothing left in the call stack or in the task queue. So I hope this illustrates why it's important to avoid functions like the super slow function that could block the call stack and thus end up blocking the entire event loop from continuing. Okay, so now let's take a look at a bit of a challenge problem. Here we have a mystery function, and we want to figure out what the order of the console logs will be. So first, we console log first, and this will get logged straight out because it doesn't have any asynchronous code, no calls to set timeout or anything like that. Then we have two set timeout calls, and we know that these will call the web API with their 1 second and 0 second delays respectively. The third one would immediately move into the task queue, but we can't call it yet since the call stack still contains mystery. Okay, so next we log out fourth, and again this one is simply a call to console log, so it logs straight out, no need to use any web APIs. And with that, the mystery function would be complete and the call stack would be empty. So this means we can dequeue the call to console log of third, and we end up logging out third next. And finally, after the second delay completes, the console log of second would be moved into the task queue, as well as pushed onto the call stack. This means the final answer would be we log out first, then fourth, then third, and finally second. Now, when talking about the event loop, these are the main concepts. However, when promises were added to the language, there was one extra component added to the picture. So now let's take a look at how we can change our model to account for this. Going back to the diagram of the runtime environment, we need to add a second queue known as the micro task queue. You will also sometimes hear this referred to as a job queue, but again, it is the same thing, just with another name. The microtask queue, for the most part, is just used to hold the callback function of promises. So anything we pass to promise.then, catch, or finally. Async and await will also use the microtask queue in the same way, as well as there's a function called queueMicrotask that we can use to manually add a callback to the microtask queue, but we don't tend to use that often. And while very similar to the original task queue, the microtask queue will follow slightly different rules. So let's revisit the event loop algorithm to include these new rules. We are still going to start off execution by dequeuing one task at a time and executing code until the call stack is empty, so the task is complete. And this is a task from the standard task queue. However, before moving on to rendering, all of the microtasks must be completed. Then only once that happens, so once the microtask queue is completely empty, the browser will render any changes, and the loop will restart by dequeuing the next task from the task queue. A simplified way to think about this is that your standard code will always run first. Running this code is essentially the first task. Then all of the promise code will run, since the microtask queue must empty itself. After this, any other callbacks, such as those from timers or DOM events, are free to run, but only one at a time. You will oftentimes see the loop written out as pseudocode that looks something like this. We loop infinitely, and in each iteration, if the task queue is not empty, we execute one task. Then after executing that task, we execute every microtask. So while the microtask queue is not empty, we execute each of the microtasks one at a time. Finally, we render any changes made to the page, and we continue the loop. So we go back to the beginning, and we would remove the next task from the task queue. Okay, so now let's take a look at an example to combine all of these concepts together and see how they interact with each other. In this code, we start by calling main, which gets added to the call stack. Then we call setTimeout with log1 and a 0-second delay. This will first be pushed onto the call stack. Then this calls the web API, which keeps track of that 0-second delay, as well as the callback function that we pass to it. So this means we can pop setTimeout off of the call stack. However, since the delay is 0, log1 can be immediately queued up in the task queue. Next, we call promise.resolve, which gets added to the call stack. This creates a new promise that is resolved to the value of 2. This promise is saved for the purpose of the chained function calls, similar to if we saved it in a variable, but the call to promise.resolve has finished, and thus it can be popped off of the call stack. Now we call the then method of that resolved promise. Since the promise is fulfilled, then is simply going to take our callback and to move it into the microtask queue. Then we'll then return a pending promise, and it can be popped off of the call stack. Next, we call then on this pending promise, passing in the console log function as the argument. In this case, we can't add console log to the microtask queue just yet because the promise is still pending, and we don't want to accidentally run this function too early. Browsers have a few internal ways to handle this, but essentially there is a list of effects that will run once a promise resolves. In this case, once the promise is resolved, the browser will enqueue this callback of console log in the microtask queue. So the important point here is just that callbacks in a then chain will not be added to the microtask queue until the previous promise in the chain resolves. Okay, so the call to then can be popped off of the call stack, and now we come to our super slow function. We push super slow function on the call stack, and we wait for it to complete. This is simply locking up the call stack and preventing any of our tasks or microtasks from running until it is done. When the super slow function finally finishes, it can be popped off the call stack. Now we can move on to the console log of 3, which gets pushed onto the call stack. We log out 3, and then we of course pop off console log of 3. At this point, main has been completed, so we pop main off of the call stack as well. And now we have a task and a microtask queued up with nothing in the call stack. If we remember the algorithm, after a task completes, we have to complete the entire microtask queue before running any more tasks. We just completed the main execution of our file, which is considered a standard task, so we must empty out the microtask queue. So this callback function that multiplies the value by 2 gets pushed onto the call stack. It will take in the resolved value of the previous promise, which was 2, and multiply by 2, giving us 4. This promise resolves, which means that the console log callback can finally be added to the microtask queue. This is also the end of our arrow function, so it is popped off of the call stack, and once again we have an empty call stack. In this case, we still have a microtask though, so we move the console log from the microtask queue onto the call stack. So even though this microtask was added far later than the task in the task queue, the microtask queue must be emptied out first. This console log will take in the value from the promise, so we end up logging out 4. This logs out to the console just like normal, and we are able to pop it off of the call stack. Now the call stack is empty once again, and the microtask queue is also empty, so we can finally move on to the next step of the event loop. The browser would render again if it needs to, Then log1 can finally be added to the call stack from the task queue. This will of course add console log of 1 to the call stack. From here, it would log out 1. Then finally, console.log would be removed from the call stack, as would the call to log1. And at this point, the call stack and both queues are empty, so our code is done running. Okay, so that's pretty much all there is to the event loop. But now to wrap things up, I want to briefly revisit why this matters and some key points here. First of all, timers are not exact. We saw that even a set timeout with 0 delay does not happen immediately in some scenarios. So if you need extremely precise timing, you will need to use date objects or the performance.now function, possibly in combination with timers to achieve that goal. In an interview setting, if you are asked a question about timers, this can be a good follow-up to make sure you are implementing your solution with the level of precision expected and demonstrating an understanding of how timers work in relation to the event loop. On a similar note, promise callbacks could also be delayed in the case that there are too many callbacks in the microtask queue, or if the call stack is waiting on another function to finish. That said, these promise callbacks do get a higher priority than event callbacks and timer callbacks. And with that in mind, you should always try to avoid any slow tasks that could block the page from working as expected. One of the easiest methods to do this is known as chunking. The idea here is to split tasks into smaller ones, usually by taking advantage of timers. In this example here, we call setTimeout with the process chunk function and no delay. We also pass 0 as an argument. Inside of the process chunk function, we process 100,000 iterations of this loop, but you would need to determine how many to process based on your own use case. Then we call another setTimeout to call process chunk again. This would keep happening until we hit this huge end value here. So the idea is that after each 100,000 iterations, by making the next chunk use setTimeout, we push it to the back of the task queue. This will free up the call stack, and it lets other tasks and microtasks clear themselves out before continuing. This can be a super powerful technique for dealing with these issues, but again, avoiding the issue altogether is usually the better bet. So anyways, with that will be the end of this video on the event loop and the concurrency model of JavaScript. I hope you enjoyed it, and I hope you learned something new. I'll see you in the next one.